Trainer, subscribers, viewers, and students, there is another video in strength of materials 2. And this is part 1. And this is about more sample problems under this topic. So problem 14, the bars of the truss each have a cross-sectional area of 800 mm square. Determine the average normal stress in member BC, BD, and DE due to the loading of P equals 40 kilonewtons. State whether the stress is tensile or compressive. So this is the figure. So let's have the free body diagram first. Remember that this truss member is a two-force body. So the force in BC is also this force here, which is expected to be in tension. At D, we have two support reactions as shown, then that is FBC also, FBC, FBC. So summation moment about D equals 0 to solve for FBC. So FBC times 0.9 equals P times 2.4 plus 0.75 times 1.2. So solving for FBC, and remember P is 40, FBC is equal to 11 over 3P. So times 11 over 3 times 40, so that's 440 over 3 kilonewtons, and we convert that to newtons. Stress in BC therefore is force over area, which is 800. So force 440 times 1000 over 3 times 800. So stress in BC is tension 183.5 megapascals tension. Then for the stress in BD, BD is this. So let's cut the truss here, this panel, and FBD would be assumed tension. That's FBD. The slope of BD would be zero point 0.9 vertical, 1.2 horizontal, which can be made 4 horizontal, 3 vertical, so 5 hypotenuse. So summation forces Y, considering forces to the left of this section and going down positive, so FBD times 3 over 5 plus P plus 0.75B equals 0. So FBD is equal to negative 35 over 12 of P, 40, so negative 350 over 3 kilonewtons. Stress in BD is 350 times 1000 over 3 times 800. That would be in megapascals, and it is in compression because the force is negative. So stress in BD is 145.8 megapascals compression. Then for force in stress in DE, this is DE. So this is the force in DE shown. So we can compute that by summing up moments about B. So FDE times 0.9 plus P times 1.2 equals 0. So FDE is negative 4/3 of 40, so negative 160 over 3 kilonewtons. Then we compute the stress, negative for 160 times 1000 over 3 times 800. It is in compression because again the force is negative. So stress in BE is equal to 66.67 megapascals. Next problem, this is problem 18. Member B is subjected to a compressive force of 3,600 newtons. If A and B are both made of wood and are 10 mm thick, determine the nearest 5 to the nearest 5 mm, the smallest dimension h of the horizontal segment so that it does not fail in shear. The average shear stress for the segment is 2 megapascals. So this is the figure, and this is critical in shearing. The force that will be transmitted there is 3,600 times 5 over 13. And we equate that to average shear stress, to the average shear stress of the segment, 2 megapascals. And the shear area is thickness perpendicular to the screen 10 mm times h. So shear force 3,600 times 5 over 13, and we equate that to 2 megapascals times shearing area. Shearing area is 10H. So 2 equals shear over shear area. For 2 times shear area, 10H equals shear force. Solving for H is equal to 69.23. So since we have to round it up to the nearest 5 mm, so the next 5 mm this is close to 70 mm. So that's it for that video. So for the next problem, 20, the joint is used to transmit a torque T of 3 kilonewton meter. So determine the required minimum diameter of the shear pin A if it is made from a material having a shear failure stress of 150 megapascals. Apply a factor of safety of 3. How about the largest torque that can be applied if the diameter of pin is 25 mm and employing the same factor of safety? So here is the given figure. Let's draw the FBD so that we can analyze the force that will be transmitted to this pin. So this is the free body diagram. The torque is, let us say, this one, applied counterclockwise. So the moment of this pin reaction should be opposite to that clockwise. So as shown, so we equate P times 100 or P times zero point 0.1 meter to the torque. So P times zero point 0.1 or summation moment about the center or about that end there or at any point equals 0. So P times zero point 0.1 equals 3 kilonewton meter. So that means P is 30 kilonewtons. So the pin, if failed, will be in single shear failure, and the working shear stress or allowable shear stress would be, since factor of safety is 3, it is equal to shear at failure or ultimate strength divided by uh, working stress or allowable stress. So therefore, it is 50 megapascals. And this 50 megapascals multiplied by the area pi over 4 diameter square, which is 25, then or pi over 4 diameter square equals, so 50 times pi over 4 diameter square in single shear equals shear force 30,000 newtons. So 50 times pi over 4 diameter square should be greater equal to 30,000 newtons. Solving for D, the minimum diameter is 27.64 mm. Then for the largest torque that can be applied if the diameter of the pin is 25 mm and employing the same factor of safety, uh, we'll have that as your exercise. Let's solve first this problem 22. The assembly consists of 3 discs A, B, and C that are used to support the load of 140 kilonewtons. So determine the smallest diameter D1 of the top disc, the diameter D2 within the support space, and the diameter D3 of the hole in the bottom disc. The allowable bearing stress for the material is 350 megapascals and the allowable shear stress is 125 megapascals. So this is the figure. So first for diameter 1. So for diameter 1, there are 2 expected failure. If it fails, one is by punching shear stress here for this member here, and the diameter is D1. The other possibility is the bearing stress that develops at this contact surface. First, let's have the punching shear. Allowable shear is 125. So it is P 125 equals P 140,000 newtons. The punching shear area is pi diameter 1 times thickness 20. So 140,000 must be less than equal to allowable shear by punching. Then punching area pi diameter 1 times thickness 20. Solving for D1, it should be greater equal to 7.83 mm. But the other possibility is at the junction between this plate and this middle plate, uh, bearing stress is possible. So 350, 140,000 equals 350. The bearing area is bearing area contact area, which is area of a circle, pi over 4 diameter 1 square. So 140,000 less than 350 times pi over 4 diameter 1 square. If bearing failure controls, so this one is, I think, greater than 17.83, so this should be the answer, 22.57 mm. Then for diameter 2, the plate is very thin, that it is only 10 mm. So a great possibility that this will fail by shearing. So 140,000 is again less than shear stress 125 times shear area pi diameter 2 times 10. 125 pi diameter 2 times 10. Diameter 2 is greater equal to 35.65 mm. Then we can check for bearing, but we need to solve for D3 first. So for diameter 3, we have only bearing stress left because the for shear, this will fail by shearing here. This cross section, remember that's a circular plate. If if this middle plate fails by shearing, by punching shear, definitely it will be this value, very small. So we investigate bearing only because if the shearing, it does not control. So if bearing controls, the bearing area is pi over 4 diameter 2 square, which we already completed, minus pi over 4 diameter 3 square. Or if we factor out pi over 4, so pi over 4 diameter 2 square minus diameter 3 square, that's the bearing area multiplied by the allowable bearing stress 350, and it should be greater than 140,000. So 140,000 less than equal to 350. Pi over 4 bearing area again is diameter 2 square minus diameter 3 square. Solving for diameter 3 is greater equal to 27.6 mm. So that's it for this video. So this is part B of problem 20. So the joint is used to transmit a torque of 3 kN meter. Determine the required minimum diameter of the shear pin A if it is made from a material having a shear failure of 150 megapascals. Apply a factor of safety of 3. How about the largest? So I answer in this video this part. This question, how about the largest torque that can be applied if the diameter of pin is 25 mm and employing the same factor of safety? So I already solved this in the preceding slide. So let's just focus on the second question. So torque is equal to P times zero point 0.1. So let's solve for P. The allowable shear stress is 50 and the diameter is 25. So P is 50 megapascals times pi over 425 mm quantity square. So torque is P times zero point 0.1 and P is 50 megapascals times pi over 425 square. That is 24,544 newtons or 24.544 kilonewtons. Substitute here, T should be less than equal to 24.544 times zero point 0.1 meter. So the unit is kilonewton meter. And that is 2.451 kilonewton meters. So that's it. That's it for this video.